Flying wings have captured the imagination of engineers and aviation enthusiasts for decades. These aircraft, which look like fancy futuristic triangles, don't have a tail or a traditional body. Instead, their entire structure is shaped like a single wing, designed to improve performance and efficiency. However, with its promise of speed, efficiency, and stealth, it's a wonder it hasn't taken over the skies. And it turns out the reasons for that are plenty. From stability issues to infrastructure hurdles, the flying wing's future is uncertain. In today's video, we're going to do a deep dive into the fascinating story behind one of the most daring aircraft designs ever conceived, and see if you could fly in one day. Flying wings are some of the most unique and futuristic aircraft ever designed. Unlike traditional airplanes, flying wings don't have a separate body or fuselage and tail. Instead, the entire aircraft is essentially one large wing. This design promises better fuel efficiency, less drag, and advanced stealth capabilities, but making them practical has been a very challenging journey. Now the idea of a flying wing isn't new, as it dates back to the early 20th century. Many aircraft pioneers were fascinated by the concept of creating a plane that was lightweight, aerodynamically efficient, and capable of carrying heavy loads. Among the first innovators was Hugo Junkers, a German engineer who developed the Junkers J-1 in 1915, a monoplane made mostly of metal. Although not a pure flying wing, his work laid the foundation for future experiments. In the 1920s and 1930s, other designers began exploring the idea more seriously. One of the most notable figures was Jack Northrop, an American engineer and founder of the Northrop Corporation. Northrop believed that flying wings were the key to achieving maximum efficiency in aviation. In 1940, his company developed the Northrop N1M, one of the first flying wing prototypes. This aircraft was small, experimental, and primarily built to test the concept. Despite its limitations, it proved that the idea was worth pursuing. During World War II, flying wings gained more attention as militaries sought ways to create faster and more efficient planes. In Germany, the Horten brothers, Reimar and Walter, designed the Horten Ho 229. This aircraft was a true flying wing and had advanced features for its time, including jet engines and stealth-like characteristics to evade radar detection. Although the war ended before the Ho 229 could be fully developed, it inspired later designs. After the war, Jack Northrop returned to his dream of building flying wings. He created several experimental aircraft, including the Northrop YB-35 and YB-49 bombers. These planes had massive wingspans and no tails, showcasing the potential of the design. However, they faced serious challenges, such as stability issues and difficulty with control. Without the advanced computers we have today, it was nearly impossible to manage the complex aerodynamics of the flying wing. Fast forward to the 1980s, and technology had finally caught up with the dream. The United States military introduced the B-2 Spirit, a stealth bomber designed as a flying wing. This aircraft became one of the most iconic examples of the design, thanks to its ability to evade radar and carry out long-range missions. Its success demonstrated that with the right technology, flying wings could be practical. However, despite these successes and improvements, there were some challenges that flying wings were faced with. One of the biggest challenges with flying wings is stability. In traditional airplanes, the tail plays a crucial role in keeping the aircraft steady during flight. The horizontal tail helps balance the airplane, preventing it from tilting too far forward or backward, which is called pitch, while the vertical tail keeps it from wobbling side to side, or yaw. Without a tail, flying wings have to rely entirely on their wing design and advanced technology to stay stable. This makes them more sensitive to turbulence and wind gusts, which can cause sudden and uncontrollable movements. For instance, if one side of the wing catches more wind than the other, the aircraft might roll or lose altitude unexpectedly. Engineers have tried to solve this issue by designing flying wings with unique shapes and by using sophisticated flight control systems. These systems rely on computers and sensors to make tiny adjustments to the aircraft's flaps and surfaces. While this helps, it also adds complexity and cost to the design. Another challenge is the complexity with its control. Controlling a flying wing is much harder than controlling a regular airplane. Traditional planes have control surfaces like elevators on the tail and rudders on the vertical fin that make it easy to climb, turn, or descend. Flying wings don't have these, so they must use other methods to maneuver. For example, flying wings rely heavily on elevons, which are control surfaces that combine the functions of elevators and ailerons, used for roll control. These elevons must work together perfectly to keep the aircraft steady. If they don't, the plane can become unstable. Another technique used is differential thrust, where the engines on either side of the wing produce different amounts of power to help steer the aircraft. However, this approach is not as precise or efficient as having a traditional rudder. The lack of a tail also makes it harder to recover from a stall. A stall happens when the aircraft loses lift, usually because it's flying too slowly or at the wrong angle. Traditional planes can use their tails to correct the angle and regain lift. Flying wings, however, don't have this option, making stalls more dangerous. Flying wings also often struggle with low-speed handling, especially during takeoff and landing. At low speeds, airplanes rely on their tails for extra stability and control. Since flying wings lack tails, they can become more difficult to manage during these critical phases of flight. For instance, during landing, the pilot must carefully control the angle and speed to avoid a rough touchdown. Without a tail, flying wings are more likely to bounce or skid if the landing isn't perfect. This makes them less forgiving than traditional airplanes. To address this, engineers have designed some flying wings with special wing shapes, like swept-back wings or curved leading edges, to improve low-speed performance. While these designs help, they still don't match the reliability of traditional airplanes. Additionally, while the sleek design reduces drag, it also limits the amount of lift the wing can produce. This means flying wings often need longer runways for takeoff and landing, which can be a problem for airports. Flying wings, while innovative and efficient, face several structural and engineering challenges that make them difficult to design and use effectively. Unlike traditional aircraft, which have a fuselage, wings, and tail for stability and control, flying wings rely entirely on their wing structure to handle everything. This unique design presents several problems related to weight distribution, structural strength, and overall durability. One of the biggest engineering challenges with flying wings is balancing weight. In a conventional aircraft, the fuselage serves as the main body, where cargo, passengers, and fuel are stored. This centralized structure makes it easier to distribute weight evenly across the aircraft. However, in a flying wing, everything must be placed within the wing itself, which complicates weight distribution. For example, passengers or cargo placed too far on one side of the wing can cause imbalances, making the aircraft difficult to control. Designers must carefully calculate where to position everything, from fuel tanks to control systems, to keep the aircraft stable. This also limits how much cargo or how many passengers a flying wing can carry, as too much weight in the wrong area could destabilize the plane. Another structural issue with flying wings is balancing strength and flexibility. Aircraft wings must be strong enough to withstand forces like turbulence, high speeds, and the weight of the aircraft itself. At the same time, they need to be flexible enough to absorb and handle these forces without breaking. In a conventional plane, the fuselage provides extra support for the wings, helping distribute the stress during flight. Flying wings, however, lack this central support. As a result, engineers must design the wings to be both incredibly strong and lightweight, a combination that's difficult and expensive to achieve. Additionally, the wide wingspan of a flying wing can make it more prone to structural stress. For example, as the wings flex during flight, they may experience uneven forces, which could lead to cracks or other damage over time. To address this, designers use advanced materials like carbon fiber composites, which are lightweight yet strong. However, these materials significantly increase production costs. Flying wings also face durability challenges, especially under high-stress conditions. Since the entire structure of the aircraft is essentially one giant wing, any damage to the wing can be catastrophic. In a conventional aircraft, damage to the fuselage or one wing might not immediately result in a total failure, as the other components can help compensate. But with a flying wing, a single structural failure could compromise the entire aircraft. The absence of a fuselage also limits how designers can optimize the aircraft for different purposes. In passenger planes, for example, the fuselage provides a clear and organized space for seating, storage, and amenities. Flying wings don't have this central structure, which means passenger seating arrangements are more restricted. Passengers would likely need to sit in rows spanning the width of the wing, which could make the interior feel cramped and less comfortable. Similarly, military flying wings face challenges in carrying weapons or other equipment. Traditional aircraft can store weapons at the fuselage or under the wings, but a flying wing must carefully integrate these systems into its structure, adding to the complexity of the design. Now, before we go to talk about other issues with this innovative concept, do like this video and don't forget to subscribe for more videos like this. Beyond the engineering and structural problems of the flying wing concept, there are also certain operational limitations that hinder its success and acceptability in the general public. The first is how incompatible they are with most airports. Flying wings have a unique shape, which can be problematic at traditional airports. Unlike standard airplanes with a clear fuselage and wings, flying wings are often much wider. This creates challenges for airport operations. For example, the Northrop Grumman B-2 Spirit, a stealth bomber with a flying wing design, has a wingspan of 172 feet. At over $2 billion apiece, this bomber required specialized facilities for maintenance. It also demanded unique hangars with specific temperature and humidity controls to preserve its stealth coating. Many airports don't have runways or taxiways wide enough to accommodate such a large aircraft. Additionally, hangars designed for conventional planes often can't store these wide-body designs, requiring costly modifications to existing infrastructure. Even for smaller flying wing concepts, the lack of a conventional fuselage can create taxiing and parking issues. Ground crews accustomed to traditional designs find it difficult to manage these aircraft, further complicating operations. Then there's the issue with payload restrictions. Flying wings have limitations when it comes to carrying passengers or cargo. The design lacks the long, centralized fuselage of traditional airplanes, which is typically used to store cargo, seats, or equipment. In a conventional aircraft, engineers can place cargo in the belly of the fuselage, leaving space for passengers above. In a flying wing, the entire payload must be distributed across the wide, flat body. This makes balancing weight a significant challenge, especially for commercial use. Improper weight distribution can lead to instability during flight. For example, NASA's X-48, an experimental flying wing, is a classic example of how difficult it is to design a balanced payload system. While it performed well in test flights, engineers struggled with layout options for passengers and cargo. These limitations make flying wings less practical for airlines, which require flexibility in how they load and arrange their planes. Maintaining flying wings is another significant operational issue. The shape and structure of these aircraft make inspections and repairs more complicated compared to conventional designs. Take the Horten-Ho 229, a German flying wing developed during World War II. Its innovative design was ahead of its time, but it proved challenging to maintain. Mechanics found it difficult to access internal components because everything was integrated into the wing. Modern designs like the B-2 Spirit have improved on this, but the problem hasn't been completely solved. Maintenance crews also need specialized training to work on these unconventional aircraft. This means higher costs and longer turnaround times for repairs, which are major drawbacks for commercial or military. Beyond all the talks of engineering and technology, let's talk about economics and how the general public might receive it. Flying wings are undeniably fascinating, but their unconventional design raises concerns for both the public and the aviation market. For most people, the idea of boarding a plane without the traditional fuselage and tail feels unfamiliar. This design doesn't look like the airplanes we've trusted for decades, which can make passengers hesitant. Safety is a top concern, and many people assume that the unique shape of flying wings might make them less reliable, even though advanced technology often ensures otherwise. From a market perspective, airlines and manufacturers are cautious about adopting flying wings. These planes don't fit neatly into existing systems, like airports and hangars, which are designed for more traditional aircraft. Retrofitting airports to accommodate flying wings would be incredibly expensive, and airlines aren't eager to take on that cost. Additionally, their unique shape can make it tricky to optimize layouts for passengers or cargo, which is a key consideration for airlines looking to maximize profits. Economics also plays a big role in the hesitation. Flying wings are often expensive to design and build due to their reliance on cutting-edge materials and advanced technology for stability and control. This higher price tag makes them less appealing to both commercial airlines and military buyers, especially when proven, reliable designs are already available. While flying wings offer exciting possibilities for fuel efficiency and stealth, their acceptance in the public and market spheres remains limited. Overcoming these perceptions will require more than just technological innovation. It will take time, trust, and proven results to make flying wings a mainstream option in aviation. In conclusion, while flying wings have always been seen as this fancy and futuristic technological design, they come with some significant challenges. From stability issues to structural concerns, and even operational limitations like airport compatibility, flying wings still face obstacles that keep them from becoming mainstream. But this doesn't mean the concept is without hope. Advances in technology are addressing some of these issues. For example, modern flight control systems powered by artificial intelligence are making it easier to stabilize and control flying wings. Lightweight, durable materials like carbon composites are also helping to overcome structural challenges, allowing for stronger, yet more flexible designs. Moreover, environmental concerns are pushing the aviation industry to explore more efficient designs. Flying wings use less fuel compared to traditional aircraft, making them a strong contender for greener aviation. Engineers are also exploring hybrid and electric flying wing concepts, which could revolutionize the way we think about air travel. Looking ahead, flying wings may not replace traditional aircraft completely, but they could play an important role in specific niches. Military stealth bombers, cargo planes, and even futuristic passenger aircraft might benefit from their unique design. In the end, the flying wing represents the spirit of innovation in aviation. It challenges conventional thinking and pushes engineers to solve complex problems. While it's not without its flaws, the flying wing shows us that the future of flight will be shaped by creativity and determination. And who knows, in a few decades, we might see flying wings soaring through our skies, proving that what once seemed impossible can become reality. And with that, we've come to the end of today's video. If you enjoyed this video and would like to learn more from the top channel on everything aircraft, do subscribe. Thank you, and we'll see you next time.